Hello everybody. This is a continuation of our notes learning how to draw Lewis structures. So we did our intro lesson. This is going to be part B, where I show you how to draw things that are covalent that only have single bonds. Later on I'll show you how to do double and triple bonds. So first, just a reminder that in a covalent bond we're going to share electrons. They may not be sharing equally. One element may be more electronegative and may tug harder on those electrons, but they are still being shared. The question is, where does each atom and each electron go in the structure? We know they're all connected. We know things are being shared. We're just trying to figure out where they are. The structure tells us a lot about how the molecules participate in reactions. So that's why we want to know what structure they have so that we can eventually know what type of reaction they undergo. So first I'm going to write an abbreviated set of our steps. Remember, your glue-in has a more extensive list, but we're going to just draw or write out our abbreviated set. So step number 1, count and sum your valence electrons. Number 2, place your atoms. Number 3, bond all atoms with single bonds. Remember, we want to assume things are simple unless we learn otherwise. Step 4, give all atoms a full shell. Remember that for most things that's 8, but sometimes it might be less, sometimes it might be more. We may not be able to do this in real life, but we're just drawing a model, right? We're just drawing on our paper. So we're going to try to give everything what it wants, and if it doesn't work, we'll fix. Step 5. Count the number of electrons, right? Those are our dots, used. And then step 6, fix if needed. That's what we'll work on another day. That's when we use our double or triple bonds. So remember, if it's too few, we're going to put them on the central atom, typically. If we used too many, that's when we're going to make double or triple bonds to fix it. So let's go back through here and just highlight the key words. Count, place, single bonds, full shell. Maybe we should say recount. Maybe that would be better, recount. And then fix. Okay, so that's kind of a brief overview. Let's off to the side here put some reminders about how we place our atoms. So remember, hydrogen goes on the outside. Remember, it kind of terminates our molecule. It's like a dead end. The next one is least electronegative. Element. Goes in the center, or the inside, however you like to think about it. Remember, in order to know which is less electronegative, we have to remember our periodic trends. Remember, francium is going to be the least, up to fluorine the most. Remember, our noble gases would technically be the least, but they don't typically like to make bonds, so we usually just think about going from francium to fluorine. And then remember, the last one is that symmetry is good. And remember, that's when possible. Which doesn't always happen. Okay? So those are our rules. Remember, they're more like suggestions. Next, what I'd like to do is kind of start with the simplest thing I can think of and go from there. So the simplest molecule I can think of would be hydrogen gas, which is H2. We have two different hydrogens, and each hydrogen comes with a valence electron. And what's going to happen is they're going to each contribute one electron, and they're going to share. So the way I draw that is I'm going to kind of squish them together. I'm color coding some of these just for the purpose of learning how to do it. I don't expect you to color code your structures on homeworks or anything. We squish them together. We keep the electrons lined up, remember, on the sides of a box. Sometimes we don't want to have to draw the dots, so we can replace them with a line. A single line is the same as 2 electrons. Okay. Now each hydrogen thinks it has 2 valence electrons. It only had 1 to begin with, but now this hydrogen feels like it has 2, and this hydrogen feels like it has 2. So they both feel more satisfied, more stable than they were beforehand. Next, let's do water, a structure we all probably know what it looks like, but now we're going to know why we set it up that way. So we have a hydrogen. Remember, it has to go on the outside. Our other hydrogen is going to go on the outside. And that leaves oxygen in the middle. Now oxygen comes with 6 electrons. You can see that I'll squish them together. The hydrogens each donate 1 electron to be shared. The oxygen donates 1 electron over here and 1 over here. If I want to redraw this in lines, I would put a line for each bond, but you're going to notice these electrons are not participating in a bond with anything. There's no atom attached here. So I do have to leave them alone. I can't put a line. I have to leave them as dots. That's called a lone pair. Oxygen has 2 lone pairs. Sometimes I'll ask you how many lone pairs a molecule has instead of looking at your drawing. It's one way we can turn things into like a multiple choice type question. So now if I look at this, this hydrogen feels like it has 2 electrons. This one feels like it has 2 electrons. And this oxygen feels like it has 8. So they all feel satisfied with their full shells. Hydrogen thinks it has 2, which is good, that's what it wants. And oxygen thinks it has 8 valence electrons, which is good. That's what it wants. Okay. Next, we're going to do a couple, and I'm going to walk us through this list of steps as we do it, so you can see kind of how I'm getting to the structure again. All right. So now let's do CF4. Well, step 1, oops, sorry about that, I'm throwing my markers everywhere. Okay, step 1 is that we need to count and sum our valence electrons. So I have 1 carbon. Carbon comes with 4 valence electrons. I have 4 fluorines, and they each come with 7. So when I add that all together, I find out that I have 32 valence electrons. Now, one thing that I like to do is realize that these typically come in pairs, and it's a lot faster to count pairs than it is individual dots. So instead of counting 32 dots, I'm going to count 16 pairs. Okay, this is covalent, right? There's no ions present here. This is called carbon, tetrafluoride. Okay. So step 2 is to place my atoms. Well, if I look at this, I have carbon and fluorine. Well, carbon is less electronegative, so I'm going to put carbon in the center. Now remember, we're trying to put everything going around on the sides of the box. And if you notice, I have 4 fluorines and I have 4 sides to my box. So I'm going to put those on the outside, 1 on each side. Another little hint, is that halogens typically will only make a single bond. They don't have to, they can do some other things, but usually they like to make single bonds. So that's another clue that I'm going to try to put them around on the outside. I'm not going to string them together in a big chain. The other thing is that if I look at the rule for symmetry, this is very symmetrical. So this is a really good way to set these up. I'm going to redraw this for the purposes of our notes. I wouldn't expect you to redraw it in a homework. So the next rule is bond all atoms with single bonds. I don't want these floating around. So they need to be connected together. Keep your dots nice and tidy on the sides of that box. Okay? Then I'm going to have step 4. Remember, I'm just redrawing this so that your notes make sense. When you go back and you look at them, you know what we did in which order. So next is give all atoms a full shell. I'm just going to give them as many electrons as they want and hope that it works. So right now the carbon is already full. It already feels like it has 8. So now I'm going to do the fluorines. It already feels like it has 2, so it just needs 6 more. And I'm going to keep them on the sides of the boxes. Make sure your dots are large enough that they are visible. Everybody likes to use these mechanical pencils, and the problem with that is your dots sometimes are not big enough to see. Especially if you're taking photos and submitting it online, you need to make sure your dots are legible. Okay? So now, all the fluorines feel like they're happy. The carbon feels like it's happy. So let's recount. We used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs, which is the same as 32 electrons, which is good, right? That's what we wanted. So we are all done. If you wanted to redraw this with lines for your bonds, you can. Okay. And that's carbon tetrafluoride. All right, let's do another one. Let's do NH3. Step 1 is count. I have 1 nitrogen. It comes with 5 valence electrons. I have 3 hydrogens that each come with 1. So altogether I have 8 valence electrons, which is the same as 4 pairs. I'm not going to recopy it over and over. We're just going to kind of do it all at once. So step 2 is to place. Well, the hydrogens have to go on the outside, which means my only other option is for nitrogen to go on the inside. I'm going to place things going around the sides of my box, spread them out. Hydrogens have to be on the outside, so that's my only option. My next step is to give everything a single bond. We don't want any atoms floating around by themselves. Step 4 is to give everything a full shell. Well, the hydrogens are full because they already have 2. Nitrogen right now feels like it has 1, 2, 3, 4, 5, 6 electrons. So it needs a couple more. So now, step 5, I used 1, 2, 3, 4 pairs, which is the same as 8 valence electrons, which is what I was supposed to do, so that's good, and we are all done. One thing to note, if you look, this nitrogen has a lone pair on it. One of the things that we're going to learn is that lone pairs can really change the shape of a molecule. So if I replace this with lines, there are my bonds. My lone pair gets left alone. Now this lone pair takes up a lot more space than a bond. The electrons are trying to repel, and so what's going to end up happening is they are going to push these hydrogens out of the way. Sometimes you may even see people draw what looks like kind of like a big, I don't know, like almost like part of a teardrop or something on top of it, showing people how much space it takes up, and the little arrows push it down. So the three-dimensional structure of nitrogen ends up a little bit different. The hydrogens end up pushed down. It distorts the shape. So that's something we'll see over and over when we start learning the three-dimensional structure of these. So instead of being flat like a pancake, what ends up happening is this NH3 ends up, it's hard to show you on the camera, it's easier in person, but it ends up looking like a three-legged piano stool, where you have the hydrogens kind of poking down, spread out equally, and then at the top is the nitrogen with its lone pair. All right, one last structure for this lesson. Sometimes you're going to notice that the formula is what we call chunked, okay? So sometimes you're going to see something like, let's see, CH3OH. And what you should notice here is that you have hydrogens in multiple places. So we have a CH3 chunk followed by an OH chunk. Oops, should do that in pink. That didn't work. Okay, good enough. So we end up with a chunked formula. That is not an official term, that's just something that I say. And a chunked formula is trying to give you a hint to the structure. Okay? A lot of times this has to do with how the molecule will behave, that it's very important for us to know that this OH is on the end of the molecule. Okay? So I'm going to kind of start setting up this chunk, and then I'm going to attach this piece, okay? So if I just look at CH3, the hydrogens have to go on the outside, and the carbon has to go on the inside. So here's my carbon. I'm going to put my hydrogens over here, so that this side of the box is left for the rest of the formula, okay? Now I'm going to connect those with a single bond so they're not floating around. And you'll notice that the carbon has one more spot available for this oxygen to come in. We know now that this hydrogen is attached to the oxygen. So this piece is one chunk, right? We have the OH part and we have the CH3 part. And now we connect these pieces together. Okay, so kind of going back to our steps, step one was to count. So I have one carbon. It comes with 4 valence electrons. I have 3 hydrogens that each come with 1. I have 1 oxygen that comes with 6. And then I have 1 more hydrogen that comes with 1. When I add that all together, I get 7 pairs in my picture, okay? I've placed my atoms by the chunking. I've connected everything with a single bond. Now my next step is to give everything a full shell. So hydrogens are already full with 2. This carbon is already full with 8, but this poor oxygen only feels like it has 4. So let's give it all the electrons at once. And now let's count and double check. I have 1, 2, 3, 4, 5, 6, 7 pairs. which is what I was supposed to have. So I'm all done. This molecule has 2 lone pairs on the oxygen. You'll notice that lone pairs tend to end up on things that are more electronegative. That's not a firm rule, but it is typical. Oxygens and nitrogens tend to like having lone pairs. If I want to replace the dots with lines, and then I make sure that my lone pairs are left as dots because they are not participating in a bond, and the line represents a bond. It is important that you are being neat and tidy and professional with your structures. I am not going to put any effort into looking at things that are so messy I can't tell what's happening. So please take, some level of pride in your work and be nice and organized. Don't try to draw teeny tiny structures. Use tons of binder paper if you need it, right? Make sure that you're using the space you need so that you can learn adequately, so that I can grade your work easily and see what you know and don't know. So please make sure you're not squishing your work and being messy with this. Okay? This is the second part. The next part will deal with double and triple bonds. All right, everybody, that's it for this part. Bye.